of Silicofeller Quantum, working on the quantum processing unit or quantum chip. Shri Manan Narang.
Hello. Yeah. So hi everyone. Thank you so much first of all to TEC for giving me this opportunity. Pawan sir, thanks so much, and all the panelists that are present here today. So it's with great honor that I would like to present to you about our developments and most importantly the quantum chips. So before going ahead, I just want to give you a brief background about why we started developing quantum chips. So a few years back, I envisioned that very soon, since there's a chip shortage that was happening at that time, so I thought that maybe sometime soon there's going to be a quantum boom, and in that quantum boom there'll be thousands and thousands of quantum computers, right? And so there'll be a shortage of quantum chips maybe. So with that in mind, I thought that okay, let's just start working on developing quantum chips and how we can make them in India or make them anywhere, but just develop quantum chips. So that's why we started Silicofeller. So Silico stands for silicon, and Feller stands for John D. Rockefeller, who was a pioneer in the oil industry. So similarly, we wanted to become the pioneers of quantum chip industry, but when we say pioneers, it means that somebody who's already doing it, and there are companies that are already doing it. So we just wanted to do something new and something innovative in India. So that's how we actually started out. So I'll start by telling you more about the first quantum revolution, right? So when we say that quantum is something new, it's not new. It's already been there, and in fact, we are living in a quantum world. It's not a classical world. We all are living in a quantum world, and I just want you to think of, we've been seeing the world in a classical sense, so we are all accustomed to it. But let me give you an honest example. If we are seeing the world with a blue color lens, we're going to see the world blue. But if we see the world from a red color lens, we're going to see the world red. So it's all about the perception, right? So I just want you all to think that it's a quantum world that we're living in, and even the phones that we are using, right? They have the transistors. They are also part of the first quantum revolution. And in fact, MRIs, lasers, GPS, they are all quantum, right? They all have some quantum nature in it. And that is how the first quantum revolution actually began. So the second quantum revolution is being led by quantum computers, right? And quantum computers is it's like the most powerful technology in the history of mankind. If you look at any single industry, the fastest growing industry has always been technology, right? And in that we have a computer that can calculate something that would take normal computers 10,000 years to do. So you can imagine how every single industry is going to get revolutionized, be it healthcare, be it automotive, be it finance. There's a revolution that is about to come that we haven't even thought of yet, and the world is about to change in unimaginable ways. So how does the stack of a quantum computer actually looks like? So these are some of the areas that that if you look at the stack, how the stack looks like, and we have tried to come in at the bottom and the top. So where we have started developing applications in quantum computing, and then at the bottom of the stack we are working on hardware design, as I told you about the quantum chips. So in between there are tests and measurements, then we have system integration, how do we build a quantum computer, then apart from that there's error correction and a whole lot of stuff that actually goes on when we are building quantum computers. So what actually can we solve with quantum computers? What are the problems that we can solve? So if you look at the three circles over there, so we need to hit at in the middle of that, where we need to find a useful problem, and we need to have no fast classical algorithm for it, and we know that there's a fast quantum algorithm. So right in the center we'll be finding the useful quantum applications, and so we can improve the polynomial improvement if we take. So these are some numbers. I'm not going to get deeper into the numbers over here, but I just want to give you a sense of how actually we can solve quantum problems and what kind of problems, as Venkat sir also discussed regarding the NP hard problems and other kind of problems. So this is where we are looking to solve some of the problems. And the solution for solving these problems, as I said, has been quantum computers. So that is why we are here today. And I'll come about our product now, about Kohinoor. So we have made India's first 4-qubit commercially available quantum chip, which is actually here displayed at our booth. So if anybody is interested to learn more about it, they can come at our booth and I can show you all about the quantum chip. So it was launched by the Ministry of Electronics. Secretary had launched it at the National Quantum Symposium along with Dr. V.K. Saraswat. So it's just a small step towards, going to thousands of qubits. So I'll tell you more about our roadmap and what exactly are we trying to do over here. But before that, let me take you into the components of a quantum chip, what actually makes a quantum chip, right? So there are a whole bunch of different parameters that are there that we need to, while we are designing quantum chips. So fabrication is different, designing is different. So there are, you can see it as an LC oscillator, and every single qubit is an artificial atom that we are creating. So we've reached a point where we can now create artificial atoms, and every single qubit is like an LC oscillator, I said. So we're just restraining it to zeros and ones. That is all that we're doing, and that is done in the block sphere. Yeah, so you can see that we send signals from the classical computer to the quantum computer. Then we have this cryogenic environment, which is called the dilution refrigerator, which is operating at ultra low millikelvin, highly cooled temperatures. So it is colder than outer space. Then we have the quantum processing unit, which is housed inside the cryogenic environment, which is called the QPU. And then we have the design of the chip, which is the physical layout. And while designing the chip, we have to do electromagnetic analysis, HFS, using HFSS, all those APR analysis, everything happens. And then quantum Hamiltonian analysis happens. And then we come to the qubit Hilbert space. So that is the final thing that in the whole picture. So this is the process flow, how we go from an actual chip design to the delivery. So first step is designing the chip, then next step is simulating the chip on actual normal computers, classical computers, then fabrication and then testing, and after that we deliver it. So what actually makes a chip better, right? There are multiple chips out there. So how do we figure out that, okay, this chip is better than the other chip? So there are three things that we need to consider. So the first one is scale, which is the number of qubits that are there inside the chip. Then comes the quality of the chip, like how good is the chip and how many circuits can it run, what is the size of the circuit that it can run. And then the speed, like how fast am I able to calculate on that chip. So with these three parameters, we benchmark the chips and figure out, okay, this chip is better than this chip. So first I'm going to talk about quantum volume, right? So I spoke about quality over here. So the scale is just a number. We can say, okay, we have X number of qubits. Then how do we determine the quality? So the quality is determined by quantum volume. And quantum volume is the largest square circuit of a random 2-qubit gate that a processor can successfully run. So what do I mean with that is, let's say we have 8 qubits, right? And the circuit depth is also 8. So it's a square. We can consider it like a square. So how many times can we actually increase the number of qubits? Let's say we go to 9 qubit and then we increase the depth to 9 before the circuit starts to give us errors, right? So let's say if we start from 1, we go to 2. So circuit with 2 depth and the number of qubits 2, then we go all the way up till 8, let's say, and we reach that, okay, we see that now we are getting the error. So we have a quantum volume of 2 raised to the power 8, which is 256. So these are some of the parameters that are there when we are considering the quality of the chip. Then next step is the CLOPS, right? Now what is CLOPS? CLOPS is circuit layer operations per second, and that is how many times can we run this quantum volume circuit and in X amount of time, let's say 100 seconds or 10 seconds. So that is how fast we've determined that. This is the parameter that helps us determine that how fast is our chip. So this is when it comes to the CLOPS, right? Now when we are designing the chips and building the chips, what are the key challenges that we face, right? So the first challenge is extending the coherence time of the chip. Then the error correction is there. Then how can we achieve high fidelity, faster gate speeds, and how can we increase the number of qubits? Can we put some qubits on one layer? Can we put the readout on the other layer? So all these things we need to consider while developing the chip, and as also the materials, like which material are we using. So this is the deployment strategy. Okay, so right now we have made 4 qubits. The world is at 1000 qubits, but the goal is ultimately 10 lakh qubits, right? So if you think that the race is still uh, not open, is if the got the winner, so it's not like that, right? Anybody can come in with a new approach and try to figure out how we can reach to 10 lakh qubits. Some people are doing it with superconducting, some are doing it with a different approach, let's say photonic qubits, ion trapped, right? So the ultimate goal is how can we get to 10 lakh qubits, right? So what we think is that if we can connect 1000 qubit processor with 1000 qubits, so that is how we can envision, like in the next 10-15 years, this is probably what's going to happen, that quantum computers will be connected with each other, right? And there's going to be a certain amount of number of qubits that we can accommodate on a chip, right? We cannot go farther than that. That is, then we'll have to connect those qubits together. So this is our roadmap. So right now we are looking to build a 27 qubit quantum chip. That is what we are doing currently. And then next year we plan on to scaling it to 127 qubits. So we don't want to build the hardware. We don't want to build quantum computers. We just want to build the chips. That is what our aim is, right? And then if somebody is building quantum computers, well and good, we can replace those quantum computers with our chips. So that is a cost effective way of upgrading the existing quantum computers and making it cost effective in the process. So that's all for the chip side. Right now I would like to also tell you more about what else we are doing. I'll just take hardly a couple of minutes more and then I'll wind up. So, and if anybody over here wants to learn quantum computing, right, I know some of you might be just starting out or some of you might be experts, but still if anybody wants to learn quantum computing, we are also teaching quantum computing. We have our mobile application using which you can start learning quantum computing. So I would suggest you all to go ahead and download the mobile application if you guys are taking out your phone. So I'll just put out the scanner in just a minute, so you can scan and download the application. So these are some of our success stories. We've trained people at GIT University, then Sharda, and then we've also signed an MOU with VIT University where we are trying to co-develop a quantum computer. So that is one exciting achievement that I would like to share with you all. And then this is the link to the application, so if you can just sign up and show your interest, that would be great, and I would be happy to entertain you at our booth. So Silicofeller, the booth, I think it's hall number booth number 9 or 8, so you can come over there. So with that, I would like to thank DSCI and NCOE for giving us for incubating us and supporting us, and also the government of India for hosting this. Thank you so much, everyone.